Happy New Year, and welcome to the first session of the seminar. Today is my pleasure to introduce our speaker, Miguel Ohnesorge, who is a British Academy postdoctoral fellow at the University of Cambridge and an incoming assistant professor of philosophy of science at Boston University. His research uses detailed historical studies of science to answer philosophical questions about measurement, evidence, and quantification. His two central projects are an epistemological history of testing Newtonian universal gravitation, which is under contract at Oxford University Press, and several comparative studies of the foundations of quantitative measurement across the sciences. Today, Miguel is going to talk about testing the universal gravitation. Please, Miguel.
Well, thank you, Dubián, for kindly introducing me, and thanks everyone for the invitation. It's really a great honor to speak here. It's a very distinguished philosophical seminar, so I'm glad you're keeping up with me. I'll try to have something interesting to say. As Dubián said, I'm going to talk about universal gravitation. It's a question mark in the title because I'm interested in a way, the scope of universal gravitation. So how universal was it? How far did we know it to generalize? And how far did the evidence that we had for that underlying theory actually go? So in doing that, sorry, there we go. In a way, trying to answer a question asked by the late George Smith, who was really I think the key figure working on Newton in the last decades, an important mentor of mine who recently passed away. And what always sort of made his work distinct is that while most philosophers of science were always interested in the failure of Newton's law and the theory change and scientific revolution to relativity, so they would ask, like Kuhn, for example, how could it even be that the law of universal gravitation turned out false after, for so many years, 230 roughly, 227? We thought it to be correct, and we tested it for all this time. What does this say about the claim that scientific theories have to knowledge? What George always thought was the interesting question was, in a way, the converse. Why is it that virtually all of the models that we build using Newton's law of gravitation, of solar system motions and planetary shapes and forces, how did those models continue to be predictively accurate after the theory turned out to be, strictly speaking, logically speaking, false? So as he writes in a sort of famous paper, he notes that the evidence from orbits, from studying orbital motions, what it showed about the accuracy of Newton's theory, how far it was accurate, remained the same, save for select exceptions, after the switch to Einstein's theory. In some places, the evidence for the specified accuracy of Newton's theory even became stronger after the switch. And there the idea is, think about Mercury's perihelion, which we needed relativity to predict. In deriving the prediction, except for this one specific detail, Einstein used all of the constants that were Newtonian for the solar system. So in a way, he tested all of these in deriving his prediction. Okay, so I'm trying to, more specifically, what I'll do, I have two main goals. One is just to sort of recover a very specific problem in celestial mechanics that's in its specificity is often forgotten. And that is testing the part of Newton's law that was actually the very controversial one, and often this is not properly spelled out, namely whether the gravitational attractions of celestial bodies is really the attraction among, the result of the attractions among their constituent parts. So that what it attracts outside causes the orbital motions around the planet is really the joint attraction of all the parts of the body. And this is the part of Newton's law we need to test to show that the attractions that we observe in astronomy and the motions we observe in astronomy are really instances of a universal force that's a property of matter, not just a property of planets or the mediums one might believe. And the answer to this lies in two interesting tests. One is deriving and measuring the figure of the Earth. I'll have a lot to say on this, and deriving and measuring its mean density. But I'm also interested in this philosophical question I already mentioned, which is trying to understand why the evidence in celestial mechanics was so stable across theory change. And in contrast to many other cases that we know from the history of science, where this was not the case. I don't think, say, Kuhn is wrong about that there are strong revolutionary changes. It's just this one seems to be a very peculiar one where lots of evidence is preserved. Why is that so? More specifically, which features of the evidential reasoning underlying the tests of universal gravitation can we use to explain that the models that we constructed based on the theory continue to, within some domain, be predictively accurate after the theory turned out to be logically false? And I'll propose a certain ideal of evidential reasoning that I think was at the heart of it. It's a norm that governed how testing worked in celestial mechanics. Okay. And I'll preclude that for you, although this will be very abstract and not very meaningful before we do the history. But the idea is roughly that what made the evidence so stable is that there's an ideal of evidential closure governing it. So you can think about it like this. If you think about a theory being a function of some parameters that gives you values for quantity, in this case x, or in the case of Newton's law, the force of gravity as a function of masses and distance between them. If we want to test for the evidential closure of a theory, we need to delineate a region within that theory's parameter space across the function, the law that the theory asserts, is sufficient to account for any empirical variations in the magnitude of x, the quantity we're predicting. So to put some meat on that, we can, of course, ask abstractly, how or whether or how strongly a theory is confirmed per se in itself. But I think if we follow this ideal, what we rather will ask is, to make it concrete in this case, across which distances or across which masses, which values of these parameters have we actually measured gravitational attractions to follow the function that the theory asserts, the function relations. That is, in this case, to be inversely proportional to the distance between bodies and proportional to the product of the masses of the bodies attracting. So, and what I mean by sufficient is that the law asserted by the theory, the functional relation, really is sufficient to specify all and only the causes that make a difference to the magnitude of the quantity, so that we only need to rely on Newton's law to explain deviations and variations in measurement, exactly in the way that the functional relation asserts. Okay, but this is very abstract, and the goal of the rest of the talk is to moderate it, and then we get back to it. Okay, so the plan is as follows. I'll talk a bit about the problem, what was tested, universal gravitation, which I already said is quite specific. It's not just the law itself, a certain part of the law. I'll then look at the history of testing it, first in the 18th century, where the main test was predicting the shape of the Earth. Then I'll look at the 19th century, where I think the logic of testing slightly changed, and the goal was no longer just to test universal gravitation simpliciter, but to delineate the scope, the evidential scope of the theory. And then I'll try to outline this ideal that I already sketched abstractly in light of that history, a certain ideal of evidential closure that I'll have a lot to say in the end. Okay, so what is universal gravitation? What is the problem of universal gravitation? How is it different from gravitation in itself? So there's a standard way of reading the argument that Newton presents in his Principia in 1687, for example, by Bill Harper in his wonderful book on Isaac Newton's scientific method. And it goes as follows. The Principia has 3 books. Book 1, Newton presents us the mathematical definitions of mass, motive forces, quantity of motions, the laws of motions, and then proves certain theorems about the relationship between forces and motions that we actually observe, say the motions of planets. So he proves, for example, that for Keplerian orbits that were known to exist, elliptical orbit with certain constants, we need a force that is inverse squarely proportional to the distance, to the center of the orbit. And then in book 3, he looks at actual orbital motions, empirical data, to show that these motions that we have in the solar system are governed by a specific law, his law of gravity. But in this reading, the argument that Newton presents appears to be incomplete. Famously, the force he tries to test is a universal force, supposed to apply to all bodies universally. But the way that this argument is usually presented, it seems as if it's tested only on the attractions of planets. So there are very specific bodies. And indeed, this is the key criticism that contemporaries had to Newton. For example, Christian Huygens, arguably back then the most important natural philosopher in continental Europe, he responded already 3 years after publication to Newton, saying that he's not especially in agreement with a principle that Mr. Newton presupposes in his calculation, namely that all the small parts that we can imagine in two or more different bodies attract one another or tend to report each other mutually. This I could not concede, nor was he at all persuaded of the necessity of the mutual attraction of all bodies, so that they attract each other. Instead, he thought, well, all Newton has shown is that if we're outside of a celestial body, there's a certain functional relation describing how much bodies accelerate as a function of distance. But that is not a universal force, just something about accelerations in the proximity of planets. And so the key distinction here is, if we look at the law, the force of gravity in its original statement, or the gravitational constant, that is more recent, it asserts that the force of gravity is proportional to the product of the mutually attracting masses, usually one is larger than the other, over the distance squared. And then there's different claims baked in the theory. Proposition 1, you can associate with a theory, which is the one that could be more easily tested and is tested in orbital astronomy, is a claim about how acceleration varies next to very massive bodies. So how much is a very small body accelerated in the proximity to a very large body? And that is what explains the orbit of a small body orbiting around a large body, like the moon around the Earth around the sun, etc. But the second claim, the claim Newton actually defended, was that his theory is not about acceleration fields outside of planets, but the acceleration fields that we observe outside of planets are actually the result of the joint and also mutual attraction of all the parts of the planets. So that the theory is a universal theory of bodies, including the ones that are the constituents of bigger bodies. And it's only by probing that second proposition that one could prove Huygens one and other critics of Newton wrong. It's only if we show that the acceleration fields are really instances of a more general law, also applying to the constituent particles of planets. And just to flag this, this is a distinction Newton himself was very aware of. People have argued, you can see it in the way he develops the argument in different steps, that he was aware that there's a huge inductive leap he's taking. And it continues to be made all into the 20th century by people like Huygens, Euler, Laplace, Kant, John Herschel, Airy, many of the people we'll re-encounter in the history, up to the 20th century. That the theory actually contained different principles. Okay, so how was this larger claim of Newton tested? And let's start with Newton himself, because as I said, Newton was aware of this problem. He was aware of it already, we know this from manuscript evidence. When he prepared the manuscript that would eventually turn into the Principia 2 years later, he realized that all the successful predictions he had derived concerned only two-body orbital system, with a small body orbiting around a very massive body, or gravitational accelerations at the surface of the Earth. So think about projectile motions or pendulums, etc. Now, these predictions, even if successful, leave undecided whether gravitation is really an interactive force. That is, whether you really need multiple masses in the numerator, or whether you just need one mass, and you see how small bodies are attracted towards that mass. So the third law of motion doesn't necessarily apply here. That's a claim that Newton made. I'm not going to talk about this a lot, although there is a substantial body of literature on that by Howard Stein and George Smith and others, because in a way, by testing the second claim that Newton didn't have evidence for initially, one also presupposes this interactivity claim. Namely, Newton's evidence at the time didn't show that gravitation really applies not only to planets, but also to their constituent parts. Okay, but if the constituent parts attract each other mutually, right, then it has to be a force of interaction, because they have to mutually attract. It has to depend on both of their masses, the force of gravitation. Okay, how did Newton come up with a test for this claim? In the summer of 1686, so this is in the process of writing the Principia, he learns about a finding by the French physicist Jean Richet, or natural philosopher, in a letter from Edmund Halley, who made a curious discovery. He had found that a pendulum clock that was calibrated to local time in Paris to complete exactly one swing in 1 second, when you took it close to the equator, to Cañas, in French Guiana back then, it lost an average of 2.5 minutes every day. Okay, so it slowed down when you took it to the equator. Well, that's very curious, because in the day, the acceleration of a pendulum, the law of free fall, as Galileo called it, was supposed to be a natural constant. So much so that it was supposed to be the foundation of a new metric system. So why did gravity vary from place to place? There was a plausible explanation in terms of centrifugal force, right? Huygens had published his theory of centrifugal motion already a few years before. And the idea is just, well, think about this. Like Cayenne at the equator, of course, the equator is further away from the axis of rotation than a place further north, like Paris. So if you think about the fact that both at the equator and in Paris, a day is completed in the same time, then to complete a longer distance in the same time, of course, it has to move at a faster velocity, the pendulum at the equator. So because of the centrifugal effect, the effective gravity, which is pulling the pendulum down, while the centrifugal effect is pulling it away from the Earth, has to be a little bit weaker. So because of the rotation of the Earth, the pendulum slows down a bit. But what Newton realized is that if that is true, it would have a lot of counterintuitive consequences, including, most prominently, that if gravity is significantly weaker at the equator, all the water would go there, right, to compensate, which is, of course, absurd. It's not the case that everything around the equator is flooded. Except if the Earth itself would be a little higher around the equator than it is around the poles. So it's slightly flattened at the poles. And then the crucial question becomes, how much higher is it? And this becomes, predicting that quantity, the ellipticity of the Earth becomes Newton's key test of universal gravitation. And to do that, he has to make mathematically precise what it means for a body to be in equilibrium, such that it avoids this differential in effective gravity. And he makes it precise with a thought experiment. The idea is, okay, how can you say that a body that's rotating is in equilibrium? Newton says, well, imagine the body would be fluid, or it would at least have two canals of fluid going from the center to the pole or to the equator. Then we have to determine in which ratio, like how long these two columns of water have to be, such that the net force of both the rotation and the mutual attraction of all its parts is exactly the same. Because it's rotating and the centrifugal effect is weakening, is acting at the equator, it has to be a bit longer around the equator to retain equilibrium. And the exact quantity by which it is longer depends on how strongly the internal parts of the Earth exert gravitational attraction, which counterbalances the centrifugal force. And that assumes mutual attraction between the parts of the Earth. Okay. And Newton famously, and this is the picture I had in the front slide, he spends a lot of mathematical effort to derive how much a slightly flattened ellipsoid that he takes the Earth to be a spheroid attracts at the equator and the poles. I'm not going to run you through the details here. Essentially, he comes up with an expression for what gravity would be in such a figure at the equator and the poles, and then he derives, knowing the empirical value of the centrifugal effect from the diameter of the Earth, he derives how much it has to be flattened, what the ratio between these two columns of water, so to speak, would be between the equator and the poles, such that it retains equilibrium. So he predicts that if the Earth constituent particles or parts attract each other according to his law, and then given the empirical magnitude of its centrifugal effect caused by its rotation, its equilibrium figure will resemble an oblate ellipsoid with an ellipticity of exactly 1/230. That's his prediction. And he proposes two measurements to test this prediction. We can test whether the Earth is flattened by this extent at the poles, either by seeing how the value of gravity changes with latitude, just as Richer had done. So we look at how a pendulum that completes a swing in a fixed period, usually 1 second, the length has to be adjusted as you go from the equator to the pole. How much does it have to be extended to compensate for the weakening of gravity or the strengthening of gravity towards the poles? Or you can just measure directly what is the difference between the length of 1 degree of a meridian. Okay, how much, if the Earth is flat at the poles, it's more curved, so 1 degree of the meridian will be longer. And Newton proposes that both of these quantities, due to the flattening of the Earth, which is derived from his law, will vary as a function of the latitude, as the sine square of the latitude, with a constant that depends on the ellipticity. That is the ratio between equator and polar axis. Okay, but the problem is Newton had no good empirical evidence. He didn't have good measurements available. On his theory, the seconds pendulum would have to be shortened by 81 over 1,000 inches in Gorée, where these measurements where other French measurements were taken, and about 89 over 1,000 inches in Cayenne, where Richer did his measurements to preserve its period relative to Paris. But these predictions were not correct. The empirical measurements, they were approximations, but they differed significantly from the existing measurements at those places. Had to be shortened more than Newton predicted. And the first measurements that were made directly of the Earth flattening, sorry, just my charger. So the changes in surface curvature in the length of 1 degree of meridian in French, they actually tended to indicated the opposite of what Newton had predicted. While on a polarly flattened Earth, you would expect the length of meridians to decrease with latitude, to increase with latitude, right? To get longer towards the poles where it's most curved because it's squashed together. They seem to decrease. So a measurement in the north of France was shorter than the one in the south of France, which seems to be, the Earth seemed to be oblong. So it's not squashed, but it's extended at the poles, which is of course a big problem for Newton's theory. And he, as you see in this little like manuscript picture I put here, Newton had this table with predictions, and he, throughout his life, throughout the 3 editions of the Principia, this is the most revised page in the Principia, this section, actually, proposition 19 and 20 of book 3, he repeatedly revised these predictions, but he never managed to accommodate the empirical evidence, despite working on it until his death. Okay. But more importantly, there's also serious theoretical shortcomings in his derivation. For one, he has to assume in his derivation of the equilibrium figure, the extent of the flattening relative to the centrifugal effect, to the rotation, that the Earth is uniformly dense, right? He assumes it's a homogeneously dense body. He doesn't have the mathematical tools to derive the equilibrium figure of a non-dense body that's rotating. And he assumes, without justifying, that the meridians are exactly elliptical when he derives the predictions for how exactly gravity and curvature change. That's a more difficult problem than predicting the ellipticity, so the ratio between the polar and the equatorial axis, which is just about the ratio of these axes, not the exact shape of the meridians. Okay. So, at least to answer the initial question of the talk, was how universal was gravitation, at least when Newton died? Well, he claimed that his law applies to all bodies universally, but the only testable predictions he had offered were for the attraction outside of celestial bodies. And these bodies were modeled as homogeneous and spherical. And for homogeneous and spherical bodies, all other competing theories of gravity could deliver equivalent predictions. The only evidence he had, the figure of the Earth, where you have a non-spherical body, the variation of attraction on a non-spherical body that depends on the law, the attraction of its part, didn't figure out. So this circumstance prevented him from testing whether the attraction of celestial bodies is really the resultant of the attraction amongst their part, which would make the law universal. Now, as I said, I'm repeating myself, this initially spurred his interest in the Earth figure, which could, in theory, offer a test, but he failed to work on a model that is strictly derivable from his law, while also being sufficient to empirically account for the measurements that were done on the Earth parameters. So at least in 1723, when the 3rd edition was published, the Principia, the law of particle-to-particle gravitation as a universal law remained a defeasible inductive generalization. Let's see how this changed in the next 100 years. Let's look at the test of the law produced by Pierre-Simon Laplace. There's a lot of stuff happening in between there. You could read my thesis and eventually my book, but I don't have infinite time. So I'm going to focus on essential bits here. Now, the first thing to say is that Laplace was, among his contemporaries, one of the most acutely aware of the empirical limits of Newton's law. So in 1776, these were his first papers. They were actually given in 1774 at the Paris Académie. He outlined the open problems, in his view, in celestial mechanics. He said we haven't certainty established that gravitation propagates instantaneously, that it acts in the same manner on bodies that rest and in motion, a very interesting one. But the one that interests me that the attractive force of a body is really the resultant of the attraction of each of the parts that compose it, the universality claim. And he notes that measurements of the figure of the Earth constitute the one set of data by which the principle of universal interparticulate attraction might actually be tested. And to test it properly, he does theoretical work. So he tries to get rid of these idealizations that still underlie Newton's test, the idealization of uniform density and of exactly elliptical meridians. And he, in the first problem, the derivation of a non-uniformly dense equilibrium figure for rotating bodies, he draws on work by Alexis Clairaut. And Clairaut has proved that you can at least derive lower and upper limits for the ellipticity of a non-uniform body, spheroidal body, so sphere-like body that's rotating, that are implied by Newton's law, independent of its density. So as long as the strata, the internal strata in the body are symmetric and the density increases inwardly, it's self-elliptical, hence elliptically symmetric, and the density increases inwardly, it can still be in equilibrium under rotation, and it will still be an ellipsoid. It will still be flattened, just as Newton said, just that it has no unique solution, but the ellipticity is bound between 1 over 230 and 1 over 577, if Newton's law is true. And he also proved that the exact value of the ellipticity among the spectrum implied by Newton's theory depends on the increase in density. So if all density is concentrated at the center, it will be 1 over 577, so less flattened. But if it's uniform, he recovers Newton's prediction. So sort of, if it's uniformly dense, we get the 1 over 230 that Newton had predicted. And he proves a theorem about how gravity, effective gravity, so minus centrifugal effect, varies as a function of latitude on the surface of such a body, by which we could then measure it. So this essentially tells us that effective gravity effective gravity at a specific latitude is equal to the GE is the gravity at the equator as a function of m being the size of the centrifugal effect as a fraction of gravity at the equator, and E being the constant for the ellipticity. And then sin squared tells us it's an elliptic function. Okay. So how does Laplace go about testing this improved theory for non-homogeneous bodies? Well, he first looks at pendulum measurements. So he takes a set of 15 measurements that were made by this time between Peru and Lapland at the extremities, at the equator and very far in the north. And he shows if the variations in the length of a pendulum beating a second, if you put them in 15 equations and solve for the best fitting value for E, when you solve these equations for the ellipticity, if it falls into the Newtonian limits, and it does. He takes the median, today we'll take the mean, and he gets 1 over 321, which is within the limits. And it implies that density increases inwardly to some extent. It's not uniformly dense. And he also showed a statistically well-behaved result. The corrections that are imposed on each of the values when computing the mean, the difference between the mean and the respective values that it implies, are well within probable observational error at the time. And he independently corroborates this by looking at the effects of the Earth's ellipticity on the Earth's rotation, which is another problem I have to skip today. Okay, well, this is a graphic error. Okay, he then goes to do the same, runs through the same with the measurements of the Earth's curvature. But he first improves the theory, as I said, to look at the case of non-perfectly elliptical meridians. So while previous derivation had to presuppose that Earth's surface is perfectly elliptical, Laplace tries to make the problem tractable for other cases. I know this gets a bit technical. The crucial theoretical advance here is his work on potential theory. So he derives an approximate expression characterizing the attraction of sphere-like bodies that can be developed for more complex bodies than spheres or ellipsoids. And this just tells you the attraction. The first term gives you the attraction of a sphere with a certain radius. And then the second term, with many subterms, tells you the changes in attraction at any point, or the changes of potential at any point, as you add further undulations to the surface of the body. So you can describe the attraction of increasingly complex bodies. And starting with this, he shows that if we take those terms into account, we can derive equilibrium figures for Earth under rotation that can be slightly non-elliptical, like slight wobbles that are protuberant above an ellipse at 45 degrees. While this effect is too small to be detected by pendulum measurements, it should appear when we measure the changes in surface curvature. And indeed, he shows it appears. There is a systematic discrepancy when he derives an ellipticity from 7 measurements, contemporary measurements of surface curvature. And he then shows that it seems like those are all concentrated around 45 degrees. Yeah, I'm not going to run you through the details here. They don't really matter. So he thinks, yeah, Newton's theory actually accounts for all the deviations that were previously recorded relative to the ellipsoidal model, because they are themselves due to the result of the gravitational attraction of the non-ellipsoidal parts of the Earth body. And it just has a more complex equilibrium figure. Okay, and he concludes that for that reason, universal gravitation is the true cause of all these phenomena. So the Earth constituent particles attract each other to Newton's law. The inequalities of the attractive forces of the planets, depending on the small irregularities in the surface and in the internal parts, we haven't previously detected them because they disappear at great distances. So if we look at astronomy, at orbital motions, the distances between the bodies are just so large that those asymmetries that depend on the internal parts of the attraction just wash out. Okay. Now, what did Laplace do? What is the evidential question underlying this test? Arguably, he asked if every discrepancy between prediction for initially simple models and then more complex models and 2 different measurements, the gravity measurements and the surface curvature measurements, are themselves the result, are themselves accountable for by Newton's theory, right? So the discrepancies from the earlier measurements prior to his improved theory, he shows, well, there were because we didn't account for the attraction of the internal strata of the Earth. But once we take this into account, we can come up with a Newtonian explanation for it. And we can actually constrain the exact difference it's supposed to make. It has to be constrained in a certain interval, and we can show it's right. The same for the parts of the Earth's surface that are not perfectly elliptical in the first approximation. These are actually, they don't violate equilibrium. Once we develop the theory further, we take into account further gravitational attractions. So he demands in his test that every discrepancy that is detected in these geodetic measurements must have physical sources that are robust, independently verifiable, and which can be sufficiently characterized by Newton's theory alone. So you cannot invoke any other explanation to give an ad hoc account for why there are discrepancies. Newton's theory itself has to be, in a way, tested again based on its ability to account for discrepancies. Now, this allows for sort of a method of successive approximation, where the evidence we get for Newton's law in every step gets stronger. Why is that so? Because with each refinement of the model, from a simple case of a uniformly dense ellipsoid to one with varying density to one with slightly more complex surfaces, the theory has to make additional predictions that presuppose the previous predictions and are constrained by Newton's law. So you cannot add something onto the model as you wish. The correction itself is constrained by Newton's law, so you're testing it another time. And this maximizes the ways in which theory could be proven wrong by empirical measurement. And this kind of testing, and this is in a way an argument George Smith has already made a long time ago, give us better evidence than a standard hypothetical deductive test. If we just derive one prediction and it agrees with the measurement, we get one test. If we derive an approximation and we show that we can then revise this approximation to account for more and more details, by just using the same theory, we test this theory several times, and each test depends on the approximate correctness of the previous one. So you get a sequence of tests that each depends on one another. And you demand that the theory is sufficient. Every discrepancy has to be accounted for by the theory. You can't invoke additional explanations. You can't say, for example, well, Newton's law would be correct, but there are all these other forces, right? I don't know, think of any, and they actually cause the Earth not to be elliptical. It's for that reason that the predictions don't work out. That is not a test of the theory. You have to show that the theory itself can account for the shortcomings of initial approximation. Okay. But note here that I had this already. Okay. This is sort of the situation as it stood in the late 18th, early 19th century. Laplace was very convinced that he had proved Newton's universal gravitation right, and he employed a very interesting logic of testing for it, this sufficiency condition of accounting for all discrepancies. But what I will show now is that the situation changed in the way the question was asked in the 19th century. For one, Laplace data turned out to be fragile, so to speak. So, for example, of the 7 measurements of surface curvature of the length of 1 degree of a meridian he used, 2 turned out to be subject to systematic errors, one in Vienna and one in Sweden, in Lapland. Had to do with, like if you do these measurements, you have to determine your latitude first. You do very precise distance measurements, but you have to know, you determine astronomically where you are in terms of latitude on the Earth to make sure you measure exactly 1 degree and you're aligned with the meridian. And there were systematic errors in the astronomical measurements, at least in the Vienna case. But also there were lots of anomalies in the variation of gravity that Laplace had not yet accounted for once more measurements with a pendulum were conducted. So Edward Sabine, an Irish-British astronomer, notes in 1823, after conducting one such survey, where he took one pendulum on a ship, and then at several places from 0 degree latitude at the island of St. Thomas up to 79 degree latitude in Spitsbergen in today's Norway. He showed that there's lots of variations that are not accounted for, and he concludes that the ellipticity that his data implies differs more considerably than could have been expected from the previously accepted. This is actually a typo. This is 336, not 306. Than could have been expected from 1/336.75, which had been previously received on the authority of the most eminent geometrician of the age, which is Laplace, as the concurrent indications of measurements of terrestrial degrees, of pendulum experiment, and of the lunar equalities dependent on the ablateness of the Earth. So there's a discrepancy between the value he gets and the value Laplace gets. But more importantly, there are a lot of anomalies, local anomalies of gravity that seem to indicate that it does not vary as a simple elliptic function of latitude. And these problems are so severe that by 1823, in his famous book on physical astronomy, in the Encyclopedia Metropolitana, John Herschel, back then perhaps the most influential British scientist, head of the Royal Society, concludes that in regards to small distances, we have no distinct proof that within a few inches or even miles from a meteorial point, the law of gravity may not begin to deviate appreciably from the Newtonian law. In fact, he goes on to say that we are at close intervals certain of the existence of attractive and repulsive forces following a widely different law. And he means sort of forces of cohesion that keep bodies together, magnetism that is just being discovered at the time. And by what imperceptible gradations these shade into that of gravity, or whether they are to be regarded as distinct from it in their nature and origin, is a point whose consideration seems reserved for a much higher state of science than we can boast of having yet attained. Now, note the conceptual difference, not only in sort of the optimism of the evidence, but in the way that Herschel states the evidential problem of testing universal gravitation versus Laplace. Now, Laplace seemed to take the evidence that he had available to decide a categorical question. Is the law of universal attraction correct? Or in his words, the true cause of the Earth's attraction and motion? Herschel rather asks, across which limits within the theory's parameter space have we actually probed Newton's law, right? He asks, across which distances have we shown it to be sufficient to account for gravitational phenomena, for motions and attractions? And what I want to argue for the rest of the talk is that as the 19th century progressed, it's the second evidential question about the scope, clearly delineating the scope of the evidence that began to take prominence in celestial mechanics. And the key text to start here is George Airy's The Figure of the Earth in 1830. It's a very technical book about the theory of equilibrium figures, as you can see here. I'm not going to run through all those differential equations, but the key point here is that he understands it as a report on the evidence at the time. In his words, it can be as a whole considered as a collection of various classes of observations which have been made for the examination of that part of the principle of gravitation which asserts that the attraction of a mass is the sum of the attractions of every one of its particles. And what Airy concludes is that he thinks it's likely that gravitation at small distances is consistent with Newton's law, but the goal now has to be to not reject observations of the existing anomalies because they disagree with theory, but it's the task of the next decades to ascertain whether they are consistent with the principle of universal gravitation. So testing has to go on. And the anomalies he means are the conflicts between the different measures Sabine had shown, but also the local anomalies that he had shown. So the fact that at specific latitudes, gravity seemed to deviate from what would be the normal on an ellipsoidal Earth. Okay. He stresses two strategies for how testing should proceed. On the one hand side, there has to be, very much in the style of Laplace, just analysis of the kinds of discrepancies in the geodetic measurements of surface curvature and gravity. So we have to ask, why and where do these strong discrepancies from theoretical gravity, as it would be expected, occur? Can we find a gravitational cause for them? And then the same, we have to ask about the errors in the measurements of the length of the meridian. And there, the relevant source of error is not literal changes in gravity, but is that changes in gravity lead to errors in the orientation of our instruments. So we'll measure the astronomical coordinates wrongly if gravity varies anomalously, because it will deflect the way that we orient our instruments. I'll tell you more about this later. But the second strategy he stresses, or the second part of his strategy for testing Newton's law, which will be very important, is also another kind of measurement. It's a measurement of Earth's mean density based on Newton's law. And you can measure Earth's mean density in different ways. You can go to the laboratory and measure how the Earth attracts relative to laboratory masses. You can measure how much the mountains attract relative to the Earth, so how much a pendulum is displaced by mountains. And you can also go down deep shafts of mines and see how gravity changes. And this will depend on changes in Earth density. And if we can show how much this is, you get the relative attraction of a small body to the Earth. And if you can show that these differences correspond to the square of the distance, you can test Newton's law at small distances. But I'll say more about this later. Okay, let's look at the first strategy. Discrepancies, further analysis of discrepancies. In the 19th century, the scope of the gravity and surface curvature measurements radically expanded. So by 1857, you have these large measurements of you can see these, maybe you can see, I hope you can see, those lines drawn on this map in 1857, those large measurements of degrees of the meridian, stretching about several degrees of latitude. You can see it two in Great Britain, one in France and Catalonia, one in the north of Germany, one in Prussia, one going all the way from the Caspian Sea to the Black Sea, from the Polar Sea to the Black Sea, one across the entirety of India, and one on the very left in today's Ecuador. So there's a lot of new measurements. Just to give you a sense of the scale of these, these were massive, massive projects. On the right, you can see the measurements of the trigonometrical survey of India by the British colonial authorities. They literally covered the entire continents in distance measurements. The way you do these measurements is you don't literally measure the distance, but you measure a very short distance, and then you embed that distance in a network of triangles. And using optical instruments, you measure the angles within those triangles, and then from the angles, having a very short measurement that's very precise, you can compute all the other distances using trigonometry. You can see here the arc going from the Polar Sea to the Black Sea. You can see the Central European arc measurements. And all of these also contain lots of stations where gravity was measured. So there's an extensive effort to collect new data on any irregularities, any deviations from an ellipsoidal model of gravity in the surface. And these are reported and collected. So this is, for example, gives you a sense, a report of 79 measurements of surface gravity by Bailey in 1834, a direct response to this debate, this problem identified by Herschel and Airy. All these people correspond. I looked into all their letters. And what is interesting about this data, I'm going to zoom in, no need to worry to read that, is there's certain systematicities in where we get deviations. What this table shows you is it gives you the latitude of a place, then it gives you the vibrations, meaning the numbers of swings that a pendulum calibrated to swing 1 second in Paris swings at this particular location. And then you get, out of all these measurements, you compute the most likely value for the ellipticity using Clause's theorem. And then you can look at the difference of the gravity that the resulting model implies and the local value you had measured, and gives you a sense of the fit of the model, right? Sort of a fit between the statistical expectation and the location relative to the model and the actual measurement. And then you can track the differences, and you can see where the differences are larger. That's then the slide next to the row next to vibrations. And notably, there's very strong differences in islands. So you can see, for example, 6 swings per day differences. I mean, this is a very precise measurements. We're talking about the difference of 6 swings over 86,000. So it's quite good measurements. And they're concentrated in islands. So you can ask, why do these? Can we come up with an explanation, a good explanation, that again probes Newton's law for why there are gravity anomalies around islands? And this is what research begins to concentrate on in the next decades. And by the end of the 19th century, we have a theory for that, the theory of isostasy. The idea is basically, it's just that if you have, in general, if you have mountains, if you have excess mass above the Earth's surface, it's compensated by a lack of density beneath them. So there's always, at some depth, an equilibrium. If you reach that depth, the total mass above it is roughly the same at any point. So any extra mass above the Earth's surface is compensated by deficits below it. And this is something that previously had not been accounted for. So in a way, these gravity measurements were overcorrected when they were measured at a certain altitude. To reduce it to sea level to make it comparable, researchers subtracted a certain amount, and this amount was just too strong because actually all the surplus mass above sea level caused much less disturbance than expected because it was compensated by density deficits below. So this was changed first at a large scale by this German geodesist Helmut in the 1880s, changes the method of reducing these observations to sea level to a common reference frame, and gets a notably smaller value for the ellipticity derived from the pendulum measurements. And a similar analysis of anomalies is done for the surface curvature measurements. There, the problem, as I said, is slightly different. Essentially, what you do when you measure these long stretches of triangles, you have to orient the telescopes at the ends that determine the relative positions of the ends of the network, and also the instruments you use to measure angles within the network. And you do that by expecting them to be perpendicular to the direction of gravity. Now, if you calculate the length of the distance in the entire network, you assume that the surface there is ellipsoidal. You're already presuming the model you're trying to test. But you can then study the deviations in the coordinates based on the best fitting surface, the best fitting elliptic surface, and the coordinates you locally determine through astronomical measurements. So you can test relative to the model how much is the direction of gravity deflected in a certain way. And this angle gives you a way to record and study these anomalies. And again, this theory of isostasy, of excess density or lack of density, deficiency of density below mountain masses, allows for a good explanation that's done by American geodesist John Hayford in the early 20th century. And he shows that if you assume, in line with the theory, that at roughly 113 kilometers, all axis mass is compensated, then the deflections in the vertical in the direction of gravity that have been recorded, in this case across North America, in 500 astronomical stations, they can all be minimized. So that provides a good test of that assumption. And it's in 1909 then that the same Hayford, he then contrasts the value he gets now from curvature measurements under this assumption with a gravity measurement that Helmut had conducted. And he notes that in view of the great confidence that Helmut placed in the gravimetric value, the one with pendulum measurements, it's important to note that the close agreement with that value and the new value he had gotten, the Coast and Geodetic Survey in America, North America. For the inverse flattening, which is 297.8, so the two values now agree within the probable error of either one, though they depend on different kinds of observations and made in different parts of the Earth. So this continuation of testing universal gravitation is very similar to the kind of work that Laplace had done. Just as before, we're asking if every discrepancy between predictions and these two different measurements can itself be explained by Newton's theory. Is itself the result of massive body solar density, say the lack of density beneath the Earth's surface, where we actually expected more density. So again, we're placing this demand that every discrepancy had to have a robust physical source, which can be sufficiently characterized by Newton's theory alone without ad hoc explanations. So far then, in the 19th century, despite this different emphasis by Herschel, evidential reasoning and geodetic measurements seem to have continued along those lines. In what sense, then, I think we need to ask now, am I correct to claim that evidential reasoning actually changed? And for that, we have to look at the other test that Airy had outlined in the 1820s. In 1830, actually, exactly. Measurements of Earth's mean density. How do you measure Earth's mean density? There's principally two ways. The basic assumption is the same. You want to measure how much a mass above the Earth's surface deflects the direction of gravity. This links back to what I said before. And you can do this by, say, looking at the deflection in a pendulum, or correspondingly an astronomical telescope, next to a massive mountain, right? And then you can see, you can from how far it is deflected, you can tell, oh, what is the ratio of the density of that mountain versus the Earth as a whole? So you can get the mean density of the Earth as a fraction of the density of the mountain. First tried in the 1740s. But you can also try to, under very controlled laboratory condition, as Henry Cavendish first does in 1798, test the attraction between a very massive, in Cavendish's case, 138 kilo ball exerts on a smaller body. And again, the smaller body, that's why I'm saying the tests are similar, it's simultaneously attracted downwards by the Earth while also being deflected to the side by a massive body. And you look at the ratio of the attractions, you get an estimate of the Earth mean density. How do you test Newton's law in these kinds of tests? Well, let's look at Cavendish's test. This is sort of his apparatus from above. It's a torsion balance. So what's happening here is you're looking from above at a balance, and you have the W's. I'm not sure I can paint here. But you see, you can see there's these two arms of the scale, and those are like the small balls that are being attracted. And then what you do is you place like this, they're being displaced. You place massive weights. These are the circles, the big circles, below them, and you see how much the balance, this balance undergoes torsion. So how much it turns in one direction, and you look at the angle it traverses. So it tells you how much over a certain time that small body is accelerated, is attracted by the bigger body. And because it's also simultaneously being attracted by the Earth as a whole, it allows you to quantify the relative attraction of the relative density of the Earth relative to the material, like to the material you're using, in this case, lead balls, or some standard that you know. Like in Cavendish's case, he knew how much denser lead balls are than water, so he could state, and this became a unit, the mean density of the Earth as a fraction of water. So the way you reason here, as I sketched below there, you take the acceleration towards the massive body W over Newton's law, sort of over the distance squared towards that body, between the balance and the body, and you compare it with the acceleration towards the Earth over the distance of the surface of the Earth towards that body, and then it gives you the ratio of the masses. Since you know the mass of the test body and you know its diameter, you can calculate its density, and you know the diameter of the Earth, you can then calculate the density of the Earth. Cavendish does this across 17 different runs of the experiment, and the mean value he arrives at is about 5.48. So the Earth is 5.48 times as dense as water. Now, the point here is as you see in this equation, here Cavendish is presupposing Newton's law. He's not testing it, right? He's calculating the density based on the distance to the surface of the Earth, so and between the balls. So he's presuming a certain variation of gravity with distance. But you can test it if you could show that in other measurements of the same kind, you get the same value for the density of the Earth. So you're testing for convergence. And this is exactly what happened over the next decades. This is a sort of a scatter plot of the results. I'm taking it from 1894 paper by Poynting, who himself conducted such a measurement. There's some serious outliers, but they're not as troublesome. For one, they're all concentrated roughly around 5.5. And the outliers all are measurements in the field, so measurements next to mountain, where there are serious uncertainties about the geological strata in the vicinity. Lots of sort of potential disturbing factors. But even this gives a surprisingly good fit. Like, we know that roughly the Earth's mean density is 5 to 7 times as large as that of water. Now, to understand the force of the evidence, now we're getting to the claim, accumulated at the end of the 19th century, one has to see those two lines of testing, these kinds of measurements at a very small scale, and the continued identification of discrepancies in the older geodetic measurements as part of the same research program, just as Airy had outlined in 1830. Because testing at these different scales allows you to make statements of the following sort. Here's Simon Newcomb in 1895 in his study of the fundamental constant of astronomy. He notes that we find that the close agreement between the density of the Earth as derived from the attraction of small masses at distances of a fraction of a meter with a density which we might a priori suppose the Earth to have, that is derived from theory, shows that within a range of distance extending from less than 1 meter to more than 6 millimeters, which is the radius of the Earth, the accumulated deviation from the law can scarcely amount to its third part. So he can make a statement about the range of distances in which we have shown the law to be sufficient to account for gravitational attractions. And the reason he's working on this, by the way, is that he's worried about the perturbations in the motion of Mercury that would eventually be the test of general relativity that Newton's law couldn't explain. So in light of this, he's asking, well, in which regions are we sure that Newton's law is correct? Where have we accounted for all discrepancies? So he sort of draws this general conclusion saying that we may therefore say with entire confidence, as a result of accurate measurement, that the law of the inverse square holds true within its 5,000th part from a distance equal to the Earth's radius to the distance of the Sun, which we know from astronomy, a range of 24,000 times, that it holds true within a third of its whole amount, which he talked about above, through the range of 6 million times from 1 meter to the Earth radius, and within a small but not yet well-defined quantity, within the distance of the Sun to that of Uranus, in which the multiplication is 20-fold. So there, sort of our evidence gets progressively weaker. But the key way that Newcomb thinks about this here is, how do we delineate the space within the parameters of the theory, within the distances, in which we have shown that the law is sufficient to account for all discrepancies? And you could find, I mean, this is sort of virtually all texts at the time argue like this. This is one of my favorite summaries of the evidence in 1919, so this is already after relativity, by Samuel Oppenheim, a Viennese astronomer. And it just shows, he's reasoning exactly in the same way, makes the same kind of statement. Okay, so as we're nearing an hour, we should get to the crucial philosophical upshots of what I've been arguing. First, a preliminary historical conclusion. So I hope to show that by the end of the 19th century, the evidential reasoning about Newton's law in celestial mechanics combines two types of questions. As already asked previously by Laplace and argued by Newton himself, as George Smith has argued, one crucial question always is if Newton's law is sufficient not only to derive initial approximate predictions, but account for all subsequent discrepancies from these approximations within empirical measurements, one after the other. This is continuously the case, as we've seen also throughout the 19th century. But there's a second question that was already explicitly asked by Herschel, which is, how exactly can we delineate the scope within the theory's parameter space in which we have tested this previous sufficiency condition empirically? So in terms of the theory, within which distances and for which masses have we actually established the sufficiency of Newton's law? So there's a second question now, which is about delineation of evidence along with the sufficiency condition. Which brings me back to this ideal, which I hope that is now a bit more intelligible, to test for what I call evidential closure. What we want to do is use the theory, the parameters across which it predicates a function, to delineate a region within the space of these parameters, so some values that they attain, across which we have shown that the law, the function, is sufficient to account for any empirical variations in the magnitudes of the quantity we're predicting, in this case, gravitational force. So if this is our ideal of evidential reasoning, we will not ask simpliciter, how strongly is a theory confirmed, but rather we'll ask across which distances and which masses have we measured gravitational attraction to be, inversely proportional to distance and proportional to the product of the masses, to accord with the relation predicated by the theory. And again, sufficiency means that we require that all and only the causes specified by the theory make a difference to the magnitude of gravitational force, and that is this difference precisely characterized and exhaustively characterized by the theory. So it's really proportional to the mass and inversely proportional to the distances. And this sufficiency clause is really just this idea. We have to account for all the discrepancies, right? We have to make the theory run through every round of further approximation as far as we can. And then we try to delineate the limits of how far we're able to push this within the language of the theory. And this gets me back, why does this ideal matter? I think it helps answer the question I posed initially, which is which features of the reasoning underlying tests in celestial mechanics explain its, for me, greatest peculiarity, the fact that virtually all Newtonian models of solar system phenomena continue to be predictively accurate within a bound domain after the transition to general relativity. I think the answer to this is that researchers, not research, not only tested predictions about universal gravitation in general, but rather they tested something more. They tested its sufficiency to account for any measured deviations, but specifically across a delineated region of the theory's parameter space that they tried to delineate empirically based on where these measurements were conducted. And I think it's this success in testing for evidential closure that gave Herschel and then Newcomb and eventually Einstein, as John Norton has shown in the sort of history of the origin of Einstein's field equation, high confidence in expecting that even if the law has to be revised, right, the future theory of gravitation, which a larger domain, will have to recover all the previous prediction of the Newtonian law within the domain where we have shown it to be empirically sufficient. And I think this contrasts quite interestingly to the other readings that philosophers, the lessons that philosophers have taken from this history, and I think that's important. For one, contra Kuhn, right? Kuhn's reading of Newtonian gravitation is that Newton's law was this has to say not. Newton's law was not substantially questioned after initially accounting for the apsidal precession of the moon in the 1740s. Instead, rather, it attained sort of a paradigmatic paradigm sort of as an exemplar. So that 19th century celestial mechanics was puzzle solving. It merely, in my reading, it did not merely concentrate on solving puzzles about its application. So this contra Kuhn, which is why I didn't say not before. Now I understand the reasoning in writing the slide. Okay, contra Kuhn, there was serious questioning about the range of the validity of Newton's law, or the scope of it. Contra Lakatos, who also heavily builds on this case, the relevant empirical success of Newton's theory is not fully characterized just by its novel predictions, but is equally characterized by the active effort to preserve its models within an empirical delineated region of its parameter space. Equally about preservation as it is about novel success. And contra George Smith, who was sort of my interlocutor in my head throughout this talk and who gave me the motivation for it, it is also not just the sufficiency. It's not just sort of this nested and robust step-by-step explanation of as many discrepancies as possible that explains the perseverance of Newtonian models across theory change, but is also the acute delineation by researchers, sort of a certain sense of healthy empiricism, if you like, to delineate the scope of such empirical sufficiency. That's an aspect of evidential reasoning that rose to prominence in the 19th century, and I think in response to many anomalies that then had turned up in regards to Newton's law. You see Herschel, for example, when he comes up, like when he first writes about these limits of Newton's law at the micro level, he draws the analogy to optics. He says, well, our laws of refraction, which we trusted for a lot of time at small distances and specific materials, they turned out to be break down. So we had to come up with a different theory of optics. Nothing guarantees that the same will not happen with Newton's law at some point. Okay. To conclude the entire talk, and I'm at 1 hour, which I'm happy about because I didn't run through this talk before. So I'm glad I'm matching the time. What I have done is revisit the history of testing Newton's argument for universal force of gravitation that applies both to celestial bodies and their parts alike. I've argued that the evidential reasoning in this history was marked by two key questions. And this already comes from Smith in a way, is always asked whether Newton's law is sufficient to derive robust sources for the discrepancies between approximations and empirical measurements, right? So it has to account not only give predictions, but account for deviations from predictions, increasingly stringently. And what exactly the scope is within the theory's parameter space in which we have tested this sufficiency condition empirically. And I think the success in answering these two questions prior to the failure of Newton's law, that is approximating what I call an ideal of evidential closure, explains why the theory's models persisted across theory change, or another way of putting this, why researchers right before and right after general relativity were so confident that they wouldn't have to revisit all the models they had constructed. And I think they were rightly confident in virtue of the merits of this method of testing and thinking about evidence. And that concludes my talk. Thank you so much for your attention.
Thank you so much, Miguel, for your talk and for sharing this interesting piece of HBS work. So let's turn to questions and answers. Please raise your hands using the Zoom button. Axel.
Oh, thank you. Oh, perdón. Miguel, in English, right? Okay.
Yeah, it's better.
Okay. Oh, thank you, Miguel. No, this was great. It was a lot of food for thought. But I am worried that maybe you have exaggerated the difference between the Laplacian epistemological approach and the Herschelian, right? Mm-hmm. Because you presented like are two very different questions that they're asking. One is whether it's right or wrong, and the other one is how to delineate the scope, right? And I'm not going to repeat it. You were very clear about it. And I was wondering whether or not you're making too much of a small difference, or even more, that the second is part of the first. The second question, because the second question seems to be the kind of questions you need to ask in order to answer the first question, right? So because you need to know what sort of evidence you have in order to know how valuable it is, right? Like how much it justifies the first hypothesis, right? Because you need to know the scope of your evidence to know what evidence you're still lacking, right? And not to keep repeating measurements of things that are blah, blah, blah. So if you think of the second question this way, the Herschelian project this way, then there doesn't seem to be that big of a difference with the Laplacian project, right? It's just maybe a more detailed description of the kind of question Laplace was doing. But you still want to make it a big deal. So can you tell us more of why the way you're reading it is rather different enough from mine to warrant thinking that it's a big difference? Please, thank you.
Yeah, thank you for your question. No, I think I won't disagree with you at all. Actually, I don't want to. I think you're right. I mean, I think if you probably, if you would have set Laplace down, and talked to him extensively and tried to push him, you can see this when he outlines the open problems in celestial mechanics. Clearly, he is aware there's a difference for the evidence we have of some parts of Newton's theory, and this part of Newton's theory he is interested in testing, the universality claim. So I don't think you're wrong. The difference is it's a difference about making explicit I think that I want to highlight. I think that what happened in the 19th century, in a way, is that there were more and more anomalies. First in this sort of terrestrial gravity research in geodesy, on the shape of the Earth, gravity of the Earth, and but these ended up being accommodated, right, as I showed, by better models. But then eventually, mid 19th century, on the motion of Mercury, and there's also ones in the Moon, and they also turn out to be accommodated, and there's Jupiter and Saturn, but the Mercury turns out to be the deadly one in a way. But as more anomalies accumulated that were studied for a long time, I think there was more of a reflection in the community of celestial mechanics about how far have we tested the law severely, so to speak. And so I think it came further this was made explicit in the conclusions in a way that it wasn't before, where the idea is, yeah, we do, like, in a way, we're testing general conclusions. And I think that matters. So I don't want to say there's a conflict, not least because I think the Laplacian way of testing, in a way, it's a Newtonian way already, as George Smith has shown, but that is crucial to what I want to say, like proper evidential closure is, right? You do want to have this strong demand of empirical sufficiency. So I don't want them to do different things. I just want the 19th century to be more explicit about the second condition. And I think it's because they were explicit about it, methodologically, that there was so much confidence towards the end of the century that the threat that the anomalies posed was limited. And Einstein shared this, right? Like when he derives this field equation, he says, well, one condition I have, that Norton's account makes this quite clear. One condition I have is they have to recover the Newtonian constants for the solar system, except Mercury, so to speak. And then, like, a few ripple effects in Venus and so on. But like that's the condition. Otherwise, that's what my theory has to do, right? So why can he be so confident? Clearly, it has to do with the fact that people have explicitly delineated the theory, so the explicitness does matter in some way. I hope that answers your question.
No, yeah, that's exactly the kind of thing I wanted.
Yeah.
Thank you.
Guadalupe, please.
Thank you very much, Miguel, for your presentation. It was wonderful. I never thought in this historical way about the notion of evidence, especially in this case of Newtonian law. But I have more philosophical questions about your presentation, especially about the notion of evidence. You, at the end of your presentation, you said some things that could be lessons that we can learn from these changes in the way that physicists understand evidence. So the first observation that I want to put here, and I want to hear your thoughts about this, is if the question about how the notion of evidence change, the same question that how universal the Newtonian law it is. I can understand how they are related, but I'm not sure that are the same philosophical question. The second thing that is really a question is how or what this teach us about the notion of evidence in physics, in a broad notion of evidence. I can understand that you show how this change in the evolution of these measurements instances, but I want to hear a little more about the philosophical notion of evidence and what lessons can we learn, especially from the last things that you said in your talk. Thank you very much, Miguel.
Yeah, thank you, Guadalupe. Thanks for the question. I'll start with the first, which was sort of more of a comment, right? Like, how are the two? I started the talk saying there are two goals. One is about recovering this problem of universality, and then the second one is thinking about evidence in the problem or evidential reasoning. Yeah, I mean you're right. Like in some sense, like the reason I chose this particular principle in Newton's law, like the universality claim, the fact that you can get the attraction of a composite body from the sum of its parts, is not one could look at another case study, so to speak. I mean, the reason I chose this one is because it was the key question in Newton's theory that remained disputed for so long, right? It was a key open question for a very long time. So I thought I think it's actually the most interesting way to study the way that in celestial mechanics, researchers conceptualized evidence. And the fact that it's a universal generalization helps, right? It always makes it interesting to ask to which extent we have tested it, which comes up because the scope of the theory, the parameter space it makes up, is infinite, if you take Newton literally. So the question is, well, what part of the parameter space then has the empirical support we want? But then to the actual question, on what does it teach us about evidence? Well, so I think, so the first thing to say is, I don't think this is necessarily very revisionist relative to sort of contemporary physics. I think much of what is good about this case, say if you look at high energy physics today, right? There's an acute awareness of thinking about the breakdown, like where our current standard model might break down, and there's acute attempts to test exactly beyond those limits. So I think I think it's quite similar. I mean, I haven't done the hard work of studying the contemporary history of high energy physics, which I think would be necessary to say that. I'm just not an expert in it, neither the physics nor the history. But I think like it seems plausible when I talk to researchers in that field that like there's a similar ideal underlying what they do. So I don't want to be revisionist. I'm not saying, oh, here are some lessons that we forgot. But I do think like nonetheless, I want to say they're important, right? There are things we can learn from these, and they're not always followed. I mean, I do think it's sometimes when philosophers think about evidence, they think about evidence, so to speak, independently of domain. They think about confirmation in the abstract, and that's especially, I think, a problem when we think about. I also work on measurement theory and so on. And like one thing that I sometimes disturbs me is when measures of confirmation or measures of evidence, right? Like there's the idea that we can just based, say, on like iterations of Bayes' theorem, we can get a measure of the degree of confirmation of a theory, and like it's not clear like what exactly we're measuring there, So in that sense, I think that there's some lessons about the importance of empirical delineation. Like it is really important to ask evidence in which range of the space across which the theory makes predictions, and then we can ask specific questions. And you can choose your favorite philosophy of statistics to ask them, but we should do it in the bounds of this. And then the second point, I guess I would say, is that this first part that I took from Smith, this idea of empirical sufficiency, that is in a way quite unique to gravitational physics. It's also not often recognized. I think the standard reading is still that the testing in celestial mechanics was and is hypothetical deductive in some way, right? But I think that doesn't get you anywhere near close to understanding the force of the evidence, because it's not deriving a prediction, say, about a planetary position and seeing is right. It's deriving a first approximation that would be true according to the theory under ideal conditions. You would have perfect Keplerian orbits in a two-body system of your homogeneous spherical bodies, and then showing that all deviations themselves have sources according to the theory. So you're testing, I went through this in the talk, but I think even that part of what I think is required for evidential closure is important to recognize as a form of testing that is distinct from standard hypothetical deductive testing based on predictions and then measuring confirmation in degrees of fit. So even there, I think there's still lessons to be learned. And I'm not saying it's necessarily what we should aspire to always. In some sense, gravitational physics is unique, I think, in that we could have that form of testing. Other forms of domains of physics, other areas of science will have different testing. Maybe you can just get normal hypothetical deductivism or something similar. But it's important to know the difference when we think about the strength of the evidence. I think that's where I'll leave it.
Thank you very much. I'm looking forward for reading your book. Thank you.
Thank you. That's very kind.
Fernanda?
Hi, Miguel. Thank you very much for your talk. I have a couple of comments. The first one has to do with evidence, and the second one has nothing to do with evidence. Well, it has to do with universality of the Newton's law. I haven't read it directly from Newton's, but in the history of science from Pierre Duhem, for example, we know that Newton claims that he was inspired in Kepler's law to derive the universal law of gravitation. And he has like these precise parts of the equation and saying why the distance, why the mass, and so on. So I was thinking that in that part of the history of science, maybe evidence has to be complemented with induction. And this is what I think is related with empirical sufficiency, because when it's insufficient, the evidence, they had to rely in the reasoning, in the induction, as Newton himself claims at the end of the Principia, right? So this is what I was thinking, that we have to say that they were confident in their equations because it was not only evidence, but also the confidence in the reasoning, in the induction, in the precise case of Newton. So that's my first comment. I don't know whether you want to say something about it, and I go to universality.
Would you like me to answer first? Then
yes,
I'll
yes.
Yeah, I mean, I think you're right. I think it's a very perceptive reading of the Principia, in the sense that I mean, and this is also just historically speaking, like the what you say about like the sort of the confidence in the induction, right? I mean, that's what Newton tries to spell out in his rules of reasoning. But the rules of reasoning are added later. They're not in the, I mean, at least the third and the fourth one. They're not in the Principia. And the reason Newton adds them is that he has to defend his generalization. The fact that he first goes from simple attraction towards a planet to mutual attraction, so the third law applying to gravity, and then the stuff that I discussed, I mean, the compositionality of attraction, because he doesn't have a test for these. They're essentially just generalizations. So, you know, like he and then there's a nice exchange between him and his editor, Coates, of the tests of the later editions. And he says, well, actually, you can't say, you know, you don't find hypotheses. And well, actually, you do, right? Like this is a hypothesis. So Newton works out a way in which, in some sense, it is like we would now call it a hypothesis. It has a different name back then. It's a sort of a supposition that the law generalizes, right? But it is not the same as coming up with a hypothesis ad hoc. And this is what the rules of reasoning sort of tell you. Why? Because you have established it somewhere. Say you know that for some forces the third law of motion applies. So you expect it to hold to gravity, right? You think like there's no principal difference between the bodies that are planets and other bodies, right? So you think they will generalize to their constituent, and so on and so forth. So I think what you're saying is exactly right. You know, there's there's crucial ingredients and all the stuff that happens in celestial mechanics is a belief in generalization. That's methodological. But it's also important to see that it's a belief that then, you know, it's a promise. It's sort of a ticket, right? So while Newton is insistent on generalizing, he's also really in his life, to the best of his you know possibilities, tries to test for empirical sufficiency, even for the things he generalized. So he doesn't take the rules sort of to be the end of the matter. Yeah, he just takes them to rule out hypotheses that are ad hoc. You know, when you explain a discrepancy by invoking another assumption or just changing the theory, you know, you should stick to the theory and make it. Yeah, okay. The second point.
I see. No, I see. Newton wouldn't be comfortable saying that, okay, I'm relying in evidence and I am also relying in induction. He always wants to prove by empirical evidence what he's claiming. So it's true. I am with you. Okay, the second point is a little bit crazy, but I had to do this question because every time I teach this part, this debate about how light goes into the water and goes faster, according to Newton, which is absolutely fake, I'm always thinking whether he wanted to say that the universal law of gravity was universal also for light particles. This is something I don't understand how he could make such a huge mistake unless he was thinking about how particles of light are attracted to each other, or probably it was something else like cohesion or magnetism. I just want to know what you think about it.
Wow, that's a good question. I don't think I can answer you. I don't know. I have to think about it. I don't know that. I mean, I know this is a famous thing, but I've never actually looked at, a bit about the optics, but I can't say I read them carefully, and I can't give you a good answer, but I'll have a look if I find
Yes,
something.
it is, well, what has to do with your topic is that if the law of gravitation is universal,
Yeah.
then universal in what sense? Only for all the bodies in the universe, or also for all the levels in the universe? That would be my question to think
No, I
in
mean,
the
he
future.
certainly believed that. Like, I can tell you that he believed that. But it would be like the interesting thing would be to figure out how would he come up with the exact magnitude. I mean, I know, for example, like these experiments, the torsion balance experiments that start in the 19th century, where you test the attraction on laboratory masses. Like Newton talks about them in the Principia, and the attraction of mountains. But he says, well, he sort of makes a calculation mistake, and he says, well, they're not detectable. He takes them to be much smaller than we now know them to be. And so I'm sort of skeptical if he thinks these are not detectable, that he would commit to sort of the gravitational effects in the light underwater, right? Like, but I'll have to think about it more. Yeah.
Okay, thank you very much.
Thank you for your comment.
Any more questions? Clarifying ones? Crucial objections?
I think Aurelia has a question.
Aurelia, okay.
Thank you very much, Miguel, for your talk. I also love the graphics. Like they allow me to follow very well, and they're beautiful. I mean, most of your talk, you were talking about the lessons we can find in history to understand more about universal gravitation. But I would like to flip the question a little bit and ask you, what does this case tell sort of about history of science? Like you mentioned, you thought this was more of a singularity, but I wonder if it would call us not only to revise in detail these historical models that we use. I mean, you mentioned Kuhn and Lakatos. But I would like to know if you think we need to go case by case when we do history of science, or if there's some general aspect that we can take when we're doing history of science, like based on this example.
Yeah, thank you. It's a fantastic question. I almost want to pass it on to Dubián, who I know has thought about this a lot in his PhD. But I do have my thoughts on this. So I mean, the first gut reaction is I think there's been a lot of emphasis in integrating history and philosophy of science more recently. I mean, at least than it has been before. And I think that's great, I mean, I also think let 1,000 flowers bloom. It's good that people do philosophy without doing history, and that's very important. But I think that one thing that within this trend, and same for philosophy of science in practice, as people often say, a certain initial motivation hasn't really been cashed out. And that is Kuhn, by all the criticism he got from me today, he said this really nicely in his, I think it's the intro to structure, where he says we have to the way we have to do, take history of science seriously is we have to learn how to think like the Aristotelian, right? Sort of this sort of first order perspective of, trying to get grabbed into the problems as they appeared in the day, and what was open, what was unresolved. And that's just a lot of work, practically speaking. You have to do the history, you have to learn the science, and have to understand how the science was seen at a but I think that's the kind of work that is more needed, for answering methodological questions, and it will be necessarily case-based, because say in my example, if I want to understand how Laplace thinks about evidence, there's no text that Laplace ever wrote about evidence or methodology even, right? So what you have to do is you have to look at what is the status of a certain claim at the time, say universal gravity, and then look at the derivations, how is he proceeding in the derivations? and then you'll learn about like his evidential reasoning. So I think, you know, isn't the only way we should do it, but I think there's one thing that it is actually very fruitful. Is one way of doing philosophy of science connected to history is really trying to think the cases through on their own terms in detail. So that's one thing, one answer. The other thing, like on the generalizations, I mean, so I do think, and that's why I was thinking of Dubián actually, like, you know, like one thing that is important is like, you know, what I've done here is sort of go through a history in detail and say how many philosophers have been wrong about what is, or not, like what they said is not complete about what makes it interesting. But clearly, you know, this is a two-way relation between history and philosophy of science. I wouldn't have been sensitive to the work that have been done if I wouldn't have been interested in a rather philosophical question. You know, what did we actually know? What was the evidence for Newton's law per se? You know, like, I mean, it doesn't seem like it seems it's a very general ahistorical question in a way, like that a philosopher would ask. You know, like historians don't, when they do their own work, they don't often ask like what is right and what is wrong, like what do we actually know. They want to know what did people think. And I think we can say more than that. We can say, for example, Newton was wrong. You know, not just what Newton believed. So, you know, I think this is a two-way street. Like philosophy really helps us, even generalizations like the ones by Kuhn and Lakatos, to focus on problems, and that then guide the way that we research history. Because without any notions, like history doesn't really work either. Like, you know, you have to make selections and you have to figure out problems and you have to focus on what is relevant about the problems. There's a nice paper by Ha-Seok Chang from 2010s, like on history as philosophy beyond case studies. I think it spells this out really nicely. There's sort of a mutually beneficial relationship between history and philosophy of science, I think. So I don't want to come over as being too critical of philosophers trying to learn from history. I mean, we need the generalizations. But if it's for me, I think within the people who commit to doing history and philosophy of science together, we could do with less generalizations and more efforts to understand the cases. At times, you know, we have to do the generalization, but perhaps less frequently. Yeah, but I'm a pluralist in the end. That's my sentiment anyway. I don't want to say people, you know, we're all colleagues. It's good that I don't get to say what others should do, because then I don't learn a lot from them. But that's my sentiment. Yeah.
Thank you.
Thanks, Dubián.
Any more questions? I would like to ask you something, Miguel. It's a basic point. Was there any relation between the concern about testing interparticle attraction or interparticle gravitation and the worry about the nature of the ontological status of gravity force? Both concerns were separated questions in the late 17th century. Can you tell us about that?
Yeah, that's like the, you know, Leibniz Clark, like the famous, like you mean like action at a distance. Like that's the question about the ontology, right? Like, is there a cause of gravitation? How that related to the generalization? Okay. Yeah, I mean, it's a good question. They're related, but definitely not identical.
No.
Like, so it happens to be that the same people who think that like sort of have a more mechanistic worldview, like Huygens, for example, who ultimately thinks, like who are quoted in the beginning, who ultimately thinks there's a mechanical explanation of gravity in the properties of the ether, right? Just he thinks Newton's right about accelerations, but then, you know, the cause of the accelerations has to do with the vortices in the ether. Just in sort of, he's more mathematically minded than other Cartesians at the time. Those people also, you know, like tend to be the ones that question the generalization. But I think the reason there is that if you think that gravity is sort of a materially mediated, it's a property of matter, it gets harder to motivate this idea of a universality, the idea that it generalizes to small bodies, because like you would like it's more natural to think, well, there's a medium, right? And like the medium through which bodies act on each other in the celestial distances is not the same. Like if there's bodies together inside of the Earth, it seems to be like a sort of a fundamentally different situation. So there's this alignment of beliefs between sort of people who like Leibniz or Huygens who question the universality, but are also like worried about the ontology. But there's like many things featuring into the ontological debate, including theological issues, right? Newton himself goes back and forth on whether he's agnostic about the cause of gravity, which he says most of the times, or whether he, as Hume will later say, there's just nothing more to say to gravity, about gravity than the law. I don't know. I think I have to think about it a bit more and do some more research. There's certainly this common motivation for thinking there's something wrong with Newton's theory, and in terms of its ontology, and in terms of the inductive generalization, which is like the role of sort of the material constitution of the medium across which, like the medium of the acceleration field, so to speak, across planets. But there's probably a more useful answer I could give if I think about it for a bit. Yeah.
Thanks. Questions? Okay, if there's no more questions, we can finish this section. Thank you very much, Miguel, for your talk, for accepting our invitation, and see you then.
Well, thanks for the invitation. It's a great honor, and it's very nice to meet many of you. I'll certainly do my research and learn about your work too. Yeah, thank you. Bye bye.